Hey, today we're going to solve this LeetCode 704 binary search. Um, so it's a very good problem. It's an easy level, and there's a whole topic in DSA that is based on the binary search. And this problem is exactly what that topic is. It's not a variation or anything. It's a very simple binary search, and it's very important because it's a foundational concept for obviously binary search questions, and even in BST or in other algorithms like where you need some binary searching or sorted arrays given and you need to find some patterns or anything like that. In that case, binary search is very helpful, and it's a very good topic as well from interviews perspective. And again, this is a very standard and a very good problem. It has 9,000 likes and only 189 dislikes, which is impressive. So let's start this problem. So we are given an array of integers, which is nums, and it's a sorted array in ascending order, and an integer target. Okay, write a function to search target in nums. If target exists, then return its index, otherwise return -1. And you must write an algorithm with log and runtime complexity. Obviously, there are basically, well, there are a lot of searches, but the two main searches are, one is linear search and the other one is binary search. Now, linear search means that you are given these numbers and you need to search, let's say 7, right? So you will start with this one and then this one, 3, 4, 5, 6, and then you will say 7. Okay, 7 is achieved, and this has a runtime complexity of linear time, that is order of n. And if you are given, so how binary search works is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now, so you have this window. In this window, the middle element is, let's say, this one, and the element that you need to find is 7. Okay, so you will say that the concentrated element is 5, the middle element, let me just write it here as middle element, and is it equal to the target? No, it's not. So you will make this observation that it's not equal to the target and it's smaller than target, which means this window, every element in this window is going to be smaller than the target. So we don't need to process this window, right? We need to only process this window, the elements on the right side of the middle element. Why? Because they will be greater than that and the target value is greater than the middle element. So we will shorten our window with this. So we'll truncate our window in this form, and in this case the middle element is this one, 7, and yeah, it is equal to 7, and we will return it that the index is equal to 6, and that is our answer. So this is how binary search works. And the runtime complexity of binary search is log n, and with the base 2. And it's, I think, very obvious to understand why it is log n base 2, because we are making truncating the segments or the windows every time with the half. So for example, in the initial step of this algorithm where we have 9 elements, we the window size was 9 elements, right? But then in the second step, in the second iteration, the 9 elements was truncated only to 5 elements, the half of it. And in the third step, even in this step, so for example we have 6, right? And this middle element was not our answer, so we will say that this middle element is, this time it is greater than the target, which means all the elements that are greater than middle element are useless. We won't be finding our target here, but we can find a target here. And in this case the window will be something like this, and in this case the third iteration we have only 2 elements. So from 9, or let's say from n, then we have n by 2 elements, then we have n by 4 elements, and then we have, and after some time, after k iterations, we will have n by 2 raised to the power k. So if you want to solve this is like a asymptotic notation topic, and if you want to solve it, after solving it, this will be something like log base 2 and runtime complexity. I mean, you don't have to specify base 2. It's a good thing to specify it, but generally in interviews and in verbal communication, we just say the log and runtime complexity. So let's see the code and how we can solve this problem. So at first we need some variables, and those variables will be the low variable, which is like the first or the beginning of the window, is equal to 0. by default will be equal to 0. Then we have high, that is equal to nums dot size minus 1. Then we need a mid element, and mid is not initialized with anything because in the first iteration from the value of low and high it will be initialized by itself. I mean, not by itself, we have to initialize it, but it will gain its value from low and high. We can initialize it here as well, it doesn't make any sense, but it won't be any beneficial. Right, now this is our binary search. So low is greater than or equal to high. If this condition satisfy, only then make the iteration, and the iteration is so low plus of high minus low by 2, and this is nothing but, this is nothing but low plus high by 2. But there can be some instances where you might encounter overflow issues, integer overflow. So to avoid them, this is the best way to write the middle value so that you won't be encountering any overflowing issues. And after this, now you have this one condition, and that is if nums of mid is equal to the target that you are looking for, then you will return that index, because mid is basically the index. Else if nums of mid is smaller than target, if the value is smaller than the target value, then so in this case, as we have already seen, so let's say the target value is 6, right? And initially we had this window and the target value was 5, right? In this case, nums of mid is less than target, right? It's less than target. So you will make this decision that every element on the left side of mid is useless, and we need to shift our window to this part, right? How we can shift our window? If this is low and this is high, that means we need to shift our low pointer, and low pointer will be moved to this part. And what is this? This is nothing but mid plus 1. So this is how we will change our value of low, and that is equal to mid plus 1. And another case is, well, we don't need else if, we can just say the else condition. And in this case, the nums of mid value, so let's say the mid value is 2, and in this case we had this whole window, right, low and high, but now the mid value is greater than this value, which means every element on the right side of mid will be greater than the mid value, and thus it will be greater than the target value, and we don't want that. We want smaller values, we want to look into the smaller values, and the smaller values can be found on the left side of mid. So to make this window possible, the low will be as it is, but high pointer will be changed, and high pointer will be here. So this is the window, and high is nothing but mid minus 1, and this is high, that is equal to mid minus 1. And after this, after our binary search is completed, the low and high pointer are either equal or low is smaller than the high pointer, then and obviously we haven't returned anything, then it means the target value is not present in nums, and if it is not, then we need to return -1 in that case, and that will be -1, return -1. So this is the code. Let's see if this will be accepted. Yes, it is. And well, it's performing, I think, okay-ish, because I have implemented the binary search, and it is log n time. Well, okay. Well, you know what, you can actually see the solution, but this is not something that the interviewer is looking for. So he is precisely looking for a binary search solution, and this is a binary search solution, and it's fine, and it's an easy level problem. You don't need to go through changing the baseline default values just to get some high, get the low runtime of an algorithm. It's fine. And yeah, so this is the problem, and thanks for watching. If you have any doubt, you can ask me in the comment section.